Hello everybody. In this video we're going to be covering section 14.2, pH and pOH. We're going to explain the characterization of aqueous solutions as acidic, basic, or neutral. We're going to express the hydronium and hydroxide ion concentrations on the pH and pOH scales, and we're going to perform calculations relating to pH and pOH. So as I alluded to earlier, the ion product of water shows that the concentration of H plus or hydronium ions and the concentration of hydroxides are inversely proportional. Okay, so if I look at that Kw product and I solve for one of them, I can see that as the concentration of protons goes up, the concentration of hydroxide ions is going to go down, and vice versa. Now we have a couple of definitions here. A solution is neutral if it contains equal concentrations of hydronium and hydroxide ions. It's acidic if it contains greater concentrations of hydronium ions than hydroxide ions, and it's basic if it contains lesser concentration of hydronium ions than hydroxide ions. So when hydroxide ions are dominating, it's basic. When hydronium ions are dominating, it's acidic, and when they're equal, it's neutral. So what is pH? We hear a lot about pH. So this is a common sort of function called the p function. Okay, and the p function is the negative log of a value. And you might wonder, why do we do this? Okay, and the reason is because this allows us to not have to deal with such large numbers and to be able to deal with numbers that have a really large span. Okay, logarithmic functions tend to compress down numbers. When you got a big span, you use a log, it kind of compresses it down into something more manageable. The negative here has to do with the fact that these are typically really dilute solutions. So you're going to have if it was just the log, all these values would be negative. We don't want that. We want them to be positive, so we use the negative there. So the pH of a solution is defined as the negative log of the hydronium ion concentration. And that's a molar concentration, so this is molarity. And then we have the pOH, which is the negative log of the hydroxide ion concentration. We don't see pOH used as much as pH, and that's because you can actually calculate the pH from the pOH, and we're going to see how we do that in a second. If we rearrange these definitions, we can solve for the hydronium ion concentration and the hydroxide ion concentration. It's 10 to the negative pH or 10 to the negative pOH. So you can see that we have an exponential relationship here, which means that we do need to be careful with our sig figs here. We need to use quite a few sig figs, otherwise we're going to have quite a bit of error. It's going to be any error will be compounded by this type of function. So we can derive a relationship between pOH and pH and pOH, and this is a good opportunity for us to remember some of our log rules. So if we start off with this Kw here, and we take the negative log of Kw, and we take the negative log of this product here, when you have a product of a log, okay, you can add those two together. Alright, so that's the negative log of the hydronium concentration plus the negative log of the hydroxide ion concentration. That's one of the log rules. Alright, so now this is pKw, this is pH, and this is pOH. So now that we have that the pKw is equal to the pH plus the pOH, we can now plug in the value of Kw at the temperature we're working at. So at 25 degrees, we know that it's 1 times 10 to the negative 14. The negative log of this value is going to be 14. So we get the pH plus the pOH at 25 degrees is equal to 14. This is going to be important for solving some of our problems in the homework and on our quizzes this week. So let's talk a little bit about neutral solutions. Neutral solutions, again, these concentrations are equal to one another. But the Kw relationship still has to hold. So if at 25 degrees, Kw is equal to this, then that means that these have to be the values of H plus and O8 and HO minus, because when you take the product of those, you get that. If we take the negative log of these, we get 7 for each of them, and that's where we get the idea that a neutral solution has a pH of 7. But that's only true at 25 degrees. Because the Kw is going to change depending on the temperature, the pH of a neutral solution is going to change with temperature. For instance, at 80 degrees, the pH of water is going to be actually slightly basic or acidic here, 6.31 and 6.31. All right. So it is important to know what a neutral solution's pH is going to be if you want to measure those, and that in particular can come into play when we're doing like different biological things like enzymatic reactions and stuff like that, where we have a slightly elevated temperature. And there are tables where you can look up the pH of a neutral solution at various temperatures. Here we have a little scale that's going to be important for solving some of our homework problems this week, where we're just relating different common materials and what their pHs are. Okay, for instance, 1 molar hydrochloric acid has a pH of about 0, whereas 1 molar NaOH has a pH of about 14, and then all these other common things that we use. So let's talk a little bit about measuring pH. There's a couple of different ways that you can go about doing this. As we alluded to earlier, there are different chemicals that will change color depending on the pH, how much acid we've added. So you can add these chemicals in and then get these different colors out, and then match those to a scale of some sort, and that'll give you a rough estimate of the pH. But sometimes we don't want to really destroy our sample, right? We don't want to have to add these indicators in there. We want to use it for something else. So another method is to actually take those chemicals and place them onto a substrate like this pH paper here, and then just take a small sample out and dab it on there. And then again, we'll see a color change and we can match it to that scale. And then there's an electronic version of this, and this is really part of the reason why we use pH over pOH. These take advantage of the fact that those protons are very small molecules, okay? And there's like a little glass membrane in these probes, and it allows those really small molecules to pass through but nothing else, and then it'll change the conductivity inside of the probe, and then you can measure that out. So this is like a more sophisticated setup you might see in like a chemistry lab or something where you're trying to be really careful. And then there's a lot of little cheapos that you can buy too, that you use for like pools or anything like that, or aquariums or something like that. That can give you a reasonable number, and you can use those. The only thing is that what winds up happening is eventually those get fouled. That little glass membrane there gets scratched up or messed up for some reason, and then you kind of got to chuck the whole thing. This has a removable probe that you can take out, and then it'll also do certain calibrations around temperature and stuff like that. So in summary, a acidic solution is going to have a hydronium ion concentration that's greater than the hydroxide ion concentration. Its pH will be less than 7 at 25 degrees. A neutral solution is going to have them equal to each other. Its pH will be 7 at 25 degrees, and a basic solution is going to have an excess of hydroxide ions, and its pH is going to be greater than 7 at 25 degrees.